microcosm.
Right now, as you sit there watching this, you're moving, not just fidgeting in your chair. You're hurtling through space at speeds that would make a fighter jet look like it's standing still. And here's the thing that'll really bend your mind. You have no idea where you're going. Let's start small. You're on Earth, rotating at about 1,000 miles per hour at the equator. That's faster than the speed of sound. But you don't feel it because everything around you is moving with you. The atmosphere, the oceans, the ground beneath your feet. It's all locked in this cosmic dance. But Earth isn't just spinning. It's also orbiting the sun at 67,000 miles per hour. Think about that for a second. Right now, in the time it takes you to blink, you've traveled about 20 miles around the sun. You're not in the same place in space as you were when you started reading this sentence. Now here's where it gets interesting. The sun isn't sitting still either. Our entire solar system is whipping around the center of the Milky Way galaxy at roughly 500,000 miles per hour. At that speed, you could circle the entire Earth in just over 3 minutes. We're on a 230 million year journey around the galactic core. The last time Earth was in this exact spot in the galaxy, dinosaurs didn't exist yet. But wait, there's more. The Milky Way itself is moving. It's falling towards something. Along with Andromeda and about 50 other galaxies in what we call the local group, we're all being pulled toward a region of space called the Great Attractor. We're moving at around 1 million miles per hour in that direction. The Great Attractor is a gravitational anomaly located about 150 million light-years away, hidden behind the zone of avoidance, that dusty part of the Milky Way that blocks our view. For decades, we couldn't see what was pulling us. We just knew something massive was out there, tugging at everything around it like a cosmic drain. Then we found something even bigger. Beyond the Great Attractor lies the Shapley Supercluster, a concentration of galaxies so massive that it contains more matter than thousands of Milky Ways combined. But even that isn't the end of the story. Our local group, the Great Attractor, the Shapley Supercluster, were all part of an even larger structure called Laniakea. Laniakea is Hawaiian for immeasurable heaven, and it's an appropriate name. This is our cosmic neighborhood, a supercluster of galaxies stretching 500 million light-years across, containing the mass of 100 million billion suns. And every galaxy in it is flowing like rivers of light toward a central basin of gravity. But here's the truly unsettling part. While gravity pulls us toward these massive structures, something else is pushing everything apart. Dark energy. The mysterious force that makes up about 70% of everything in the universe is causing space itself to expand, and it's accelerating. Imagine blowing up a balloon with dots drawn on it. As the balloon expands, the dots move apart, not because they're traveling across the surface, but because the surface itself is stretching. That's what's happening to our universe. Galaxies aren't just moving through space. Space is growing between them. This means that while we're falling toward Laniakea's center, distant galaxies outside our supercluster are moving away from us faster and faster. Some are already moving away faster than the speed of light. Not because they're breaking the cosmic speed limit, but because the space between us is expanding faster than light can cross it. Think about what that means. There are galaxies we can see right now, their light having traveled billions of years to reach us, that we will never, ever be able to visit. Even if we could travel at the speed of light, we could never reach them. The expansion of space has already carried them beyond an invisible horizon, a cosmic point of no return. So where is everything moving? The answer is in every direction at once. Locally, gravity wins. Galaxies cluster together, pulled by their mutual attraction. Our local group, Laniakea, even larger structures like the Pisces-Cetus supercluster complex, they're all held together by gravity, swirling and merging in slow-motion collisions that take hundreds of millions of years to complete. In fact, Andromeda, our nearest large galactic neighbor, is heading straight for us at about 250,000 miles per hour. In about 4.5 billion years, our galaxies will collide. Not like cars crashing, stars are too far apart for that. But the galaxies will merge, their shapes distorted by gravity, their spiral arms stretched and torn, eventually forming one giant elliptical galaxy. Some astronomers have already given it a name, Milkomeda. But on the largest scales, beyond the gravitational reach of our local structures, expansion dominates. The universe is being pulled apart. Galaxy clusters are drifting away from each other, accelerating into the darkness, and there's nothing that can stop it. Here's something that should make you pause. We can only see galaxies whose light has had time to reach us since the Big Bang. That's a sphere about 93 billion light-years across, what we call the observable universe. But the actual universe is bigger, possibly infinite, and most of it is moving away from us so fast that we'll never see it. We're living in a shrinking island of visibility. Every day that passes, more galaxies cross that horizon and disappear from view forever. If you could fast forward 1 trillion years, the sky would be almost empty. Future civilizations, if any exist, would see only the merged remains of our local group, surrounded by darkness. They might conclude they're alone in the universe, never knowing about the billions of galaxies that once filled the sky. But let's bring this back to you sitting there right now. You're on a planet spinning at 1,000 miles per hour, orbiting a star at 67,000 miles per hour, in a solar system racing around a galaxy at 500,000 miles per hour, in a galaxy falling toward the Great Attractor at 1,000,000 miles per hour, all while the fabric of space itself expands, carrying distant galaxies away from us at speeds we can barely comprehend. Add it all up, and your motion through space is breathtakingly complex. There's no universal reference frame, no cosmic GPS that can tell you where you really are or how fast you're really moving. Motion is relative. It only makes sense compared to something else. Einstein taught us that when you're in an airplane cruising at altitude, you can't feel the motion. You could be standing still or moving at 600 miles per hour, and without looking out the window, you'd never know the difference. The same principle applies to our motion through the cosmos. We're moving at incredible speeds, but we don't feel it because we're moving with everything around us. So what does all this motion mean? Why is everything moving? The answer goes back to the beginning, to the Big Bang. About 13.8 billion years ago, the universe began in a state of extreme density and temperature. It wasn't an explosion in space. It was an explosion of space. And from that first instant, everything has been moving apart, expanding, cooling, forming structures along the way. But the expansion wasn't perfectly smooth. Tiny quantum fluctuations in the early universe, variations in density smaller than an atom, were stretched by cosmic inflation into the seeds of galaxies. Where density was slightly higher, gravity pulled matter together. Where it was slightly lower, matter flowed away. Over billions of years, those tiny ripples grew into the cosmic web we see today. Vast filaments of galaxies separated by enormous voids. And we're still seeing the echoes of that ancient beginning. The cosmic microwave background radiation, the afterglow of the Big Bang, shows us a snapshot of the universe when it was just 380,000 years old. It's covered in tiny temperature variations, and those variations map perfectly onto the large-scale structure of the universe today. The hot spots became galaxy clusters. The cold spots became voids. Everything in motion now, every galaxy, every star, every atom, is following trajectories set in motion billions of years ago. We're all riding the momentum of creation itself. But motion in the universe isn't just about where things have been. It's about where they're going. Remember dark energy? That mysterious force accelerating the expansion of the universe? We don't know what it is. We can measure its effects, see how it's pushing space apart, but we have no idea what causes it. It might be a property of space itself, a cosmological constant that Einstein once proposed and then rejected. It might be a new kind of energy field pervading the universe. Or it might be something we haven't even imagined yet. What we do know is that it's winning. Gravity can hold together galaxies and galaxy clusters, but on larger scales, dark energy dominates. And as time goes on, its influence grows stronger. This leads to a strange future. As the universe continues to expand and accelerate, galaxy clusters will become isolated islands in an ocean of expanding space. Eventually, even the light from nearby clusters won't be able to reach us. The sky will go dark. Stars will continue to form for a while from the remaining gas, but eventually that will run out too. Stars will die and not be replaced. In about 100 trillion years, the last stars will flicker out. The universe will be filled with dead stars, black holes, and cold darkness. Even the black holes will eventually evaporate through Hawking radiation, a process that takes an incomprehensible amount of time. We're talking 10 to the 100th power years. That's a 1 followed by 100 zeros. After that, the heat death, a universe at maximum entropy, where no energy flows, no work can be done, and nothing interesting can ever happen again. Just a cold, dark, empty expanse of space, expanding forever. It's a bleak picture, but it's also trillions of years away. For now, we live in what some cosmologists call the stelliferous era, the age of stars. Galaxies are still forming, stars are still being born, planets are still coalescing from disks of dust and gas. Life, at least here on Earth, is thriving. And we're moving, always moving. There's something profound about that. We like to think of ourselves as the center of things, anchored and important. But the universe doesn't care about centers. There is no center. Every point in space is expanding away from every other point. If you were in a galaxy 10 billion light-years away looking back at us, you'd see the same thing we see, galaxies receding in all directions. We're not special in terms of location, but maybe that's exactly what makes us special. In a universe of relentless motion, of galaxies fleeing into darkness, of stars being born and dying, we exist. We're here on this small blue world, asking questions about our place in all of it. And we're figuring it out. 100 years ago, we didn't even know other galaxies existed. We thought the Milky Way was the entire universe. Then Edwin Hubble pointed his telescope at what we thought were nebulae and discovered they were galaxies, billions of light-years away. And they were all moving away from us. That single observation changed everything. It told us the universe was expanding. It led us back to the Big Bang. It revealed the universe has a history, a beginning, and a future. Since then, we've mapped the cosmic web, discovered dark matter and dark energy, measured the age of the universe to within a few million years, and traced our motion through space with incredible precision. We've sent spacecraft beyond our solar system, carrying messages for anyone who might find them, even though we know those craft are moving slower than the galaxy itself. We've done all of this in less than a century of serious cosmological study. Imagine what we'll know in another 100 years. But here's something to consider. Our understanding of cosmic motion has practical consequences. GPS satellites, for example, have to account for relativistic effects. Time runs slightly faster in orbit than on Earth's surface because of gravity and motion. If we didn't correct for that, GPS would drift by miles every day. The equations that describe how galaxies move are the same ones that keep your navigation working. And on a deeper level, understanding where everything is moving helps us understand where we came from. The atoms in your body were forged in stars that lived and died billions of years ago. Those stars were part of galaxies that collided and merged. The iron in your blood, the calcium in your bones, the carbon in your DNA, all of it was created in stellar furnaces and scattered across space in supernova explosions. You are made of star stuff, as Carl Sagan famously said. And that star stuff has been moving through the universe for billions of years before coming together to form you. So where is everything moving? Toward an uncertain future in an expanding universe. But also, in a very real sense, toward us. Toward this moment. Toward consciousness and curiosity and the ability to look up at the night sky and ask these questions. The universe is vast and indifferent, governed by physical laws that operate on scales we can barely comprehend. but it's also somehow given rise to beings who can understand it, who can trace the motion of galaxies, predict the collision of black holes, and wonder about what lies beyond the edge of the observable universe. We're moving through space at incredible speeds, caught up in flows of gravity and expansion that have been in motion since the dawn of time. We can't stop it, we can't change it, but we can understand it. And in understanding it, we find our place in the cosmos. Not at the center, not special by location or motion, but special because we're here to witness it all, to measure it, to marvel at it. Every second, you travel thousands of miles through space without even trying. Every moment, the universe grows larger, more distant galaxies cross the horizon, stars are born and die. The cosmos is in constant flux, a dynamic, evolving system of unimaginable complexity. And somehow, against all odds, in one small corner of an ordinary galaxy, on an unremarkable planet orbiting an average star, life emerged. And that life became conscious, and that consciousness looked up and asked, "Where are we going?" The answer is still being written. With every new discovery, every refined measurement, every telescope pointed at the distant universe, we learn more about our cosmic journey. We're not passive passengers. We're explorers, cartographers of space and time, mapping the currents that carry us through the void. So the next time you look up at the night sky, remember, those stars aren't fixed in place. They're moving. We're moving. Everything is moving. And in that motion, in that endless cosmic dance, there's a beauty that transcends the bleakness of eventual heat death or the loneliness of an ever-expanding universe. Because right now, in this brief moment of cosmic history, we're here, moving through space at 1,000,000 miles per hour, pulled by gravity, pushed by dark energy, spinning and orbiting and falling through the darkness. And we know it. We understand it. We can calculate it, predict it, and appreciate it. That's not nothing. In a universe where most matter is dark and most space is empty, where galaxies flee into the void and stars burn out, the fact that we exist and can comprehend our place in it all is extraordinary. We are the universe becoming aware of itself. Billions of years of cosmic evolution, of star formation and planetary accretion, of chemistry and biology and natural selection, all leading to this, a species that can trace its motion through space back to the Big Bang and forward to the heat death of the cosmos. Where is everything moving? Toward complexity, toward structure, toward life and consciousness, even as it moves toward entropy and dissolution. The universe is both constructive and destructive, creative and chaotic, building up and tearing down simultaneously. And we're part of that. Our motion through space isn't separate from us. It's fundamental to who and what we are. The energy that drives our cells, the light that lets us see, the heat that keeps us warm, all of it traces back to the motion and transformation of matter and energy throughout cosmic history. So embrace it. You're not standing still. You never have been. You're a traveler through space and time, riding currents set in motion at the dawn of creation, headed toward a future we can only begin to imagine. Where is everything in the universe moving? Forward, always forward, into the unknown, into the darkness, into tomorrow. And that's exactly where we need to go. Let's talk about something that doesn't get enough attention: the cosmic web. If you could step outside the universe and look at it from a distance, you wouldn't see galaxies scattered randomly through space. You'd see structure, vast filaments of galaxies stretching across hundreds of millions of light years, connected by tendrils of dark matter, surrounding enormous voids where almost nothing exists. It looks organic, like neurons in a brain or the mycelial network of fungi spreading through soil. The largest structures in the universe mirror the smallest in ways we're only beginning to understand. And everything in this web is moving, flowing along these filaments like blood through veins. The Sloan Great Wall is one of these structures. Discovered in 2003, it's a cosmic filament containing billions of galaxies stretching across 1.3 billion light-years. that's so large that light takes over 1 billion years to cross from one end to the other. And it's moving. The entire structure is participating in the cosmic flow, pulled by gravity, pushed by expansion. Then there's the Hercules Corona Borealis Great Wall, even bigger at 10 billion light-years across. To put that in perspective, that's about 10% of the diameter of the observable universe. A single structure so massive it challenges our understanding of how the universe formed. According to our models, there shouldn't be enough time since the Big Bang for something that large to have come together. But there it is, moving through space like everything else. These structures tell us something crucial about the early universe. Remember those quantum fluctuations we talked about? Tiny variations in density when the universe was younger than a second old? They weren't distributed evenly. There were patterns, scales, frequencies, like notes in a cosmic symphony. When cosmologists analyze the cosmic microwave background, they're looking at those patterns. They can measure the size of the hot and cold spots, the way they're distributed across the sky, and from that, they can work backward to figure out what the universe was like in its first moments. It's like listening to the echo of a sound and reconstructing what made it. What they've found is remarkable. The universe had acoustic oscillations, sound waves, pressure waves traveling through the hot plasma that filled space before atoms even existed. These waves created regions of slightly higher and lower density, and when the universe cooled enough for atoms to form, those density variations became frozen into the structure of space. Gravity then took over. High-density regions attracted more matter. Low-density regions lost matter. Over hundreds of millions of years, those tiny variations grew into the cosmic web we see today. The galaxies, the filaments, the voids, all of it traces back to sound waves in the infant universe. And those sound waves are still affecting how things move today. The baryon acoustic oscillation, as it's called, left a characteristic scale imprinted on the universe. Galaxies tend to be separated by about 500 million light-years because of it. It's like the universe has a preferred wavelength, a resonant frequency from its earliest moments. We use this to measure cosmic distances and expansion rates. By looking at how galaxies cluster, we can determine how much the universe has expanded since the light left them. It's one of our most powerful tools for mapping the cosmos and understanding where everything is headed. But here's where it gets weird. Not all motion in the universe follows the predictions. There are peculiar velocities. Most galaxies are moving away from us because of cosmic expansion. That's called Hubble flow. But galaxies also have their own individual motions, pulled by nearby massive objects or falling into galaxy clusters. These peculiar velocities can be hundreds of miles per second in seemingly random directions. The problem is, when we measure these velocities across large volumes of space, we find patterns that shouldn't be there. There's a bulk flow, a coherent motion of galaxy clusters over scales of hundreds of millions of light-years, all moving in roughly the same direction. Some astronomers call it the dark flow. Clusters of galaxies moving toward a particular region of space at nearly 2 million miles per hour, and we don't know why. The Great Attractor can't explain it. Laniakea can't explain it. Whatever is pulling these galaxy clusters is beyond our observable universe, beyond the cosmic horizon. Think about what that implies. There's something out there, beyond the edge of what we can see, massive enough to affect the motion of thousands of galaxies across billions of light-years. We can't see it. We'll never see it because its light hasn't had time to reach us and never will. But we can infer its existence from the way galaxies move. It's like feeling a current in water and knowing there must be something downstream causing it, even though you can't see that far. The universe is bigger than the observable universe, and what lies beyond is influencing what happens inside. Not all scientists agree on dark flow. Some measurements confirm it, others don't. It's possible there are systematic errors in how we measure these velocities, or that we're misinterpreting the data. But if it's real, it means our understanding of cosmic structure is incomplete. There are forces and masses beyond our horizon that we're only detecting through their gravitational influence. And that brings us to dark matter, the invisible scaffolding of the universe. Galaxies rotate too fast. If they contained only the matter we can see, the stars, gas, and dust, they would tear themselves apart. The outer regions of spiral galaxies orbit the galactic center at speeds that require far more mass than we observe. But they don't fly apart. Something is holding them together. That something is dark matter. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all. We can't see it directly, but we can see its effects. Galaxies embedded in halos of dark matter, clusters of galaxies held together by dark matter's gravity. Even the cosmic web itself is structured by dark matter filaments. About 85% of the matter in the universe is dark. Only 15% is the ordinary matter that makes up stars, planets, and us. We're the minority. The universe is dominated by something we can't detect except through gravity. And dark matter is moving. Like everything else, it's caught up in cosmic flows, falling into gravitational wells, clustering around galaxies. Computer simulations of structure formation show that dark matter moved first. In the early universe, before the first stars formed, dark matter was already clumping together, creating gravitational wells that normal matter fell into. Those dark matter halos became the seeds of galaxies. Where dark matter clustered, gas accumulated. The gas compressed, heated up, and eventually formed stars. Galaxies grew inside dark matter halos like pearls forming around grains of sand. Without dark matter, galaxies wouldn't exist. The universe would be a diffuse fog of hydrogen and helium, never dense enough to collapse and form stars. We owe our existence to this mysterious, invisible substance that outweighs normal matter 5-1. But what is it? That's one of the biggest unsolved questions in physics. It could be exotic particles that barely interact with normal matter. WIMPs, weakly interacting massive particles, are a popular candidate. Or maybe axions, hypothetical particles predicted by quantum physics. Or perhaps it's primordial black holes, formed in the first moments after the Big Bang. Dozens of experiments around the world are trying to detect dark matter directly. Sensitive detectors deep underground, shielded from cosmic rays, waiting for a dark matter particle to collide with an atomic nucleus. So far, nothing definitive. Dark matter remains elusive, but we know it's there, and we know it's moving. The Bullet Cluster proves it. Two galaxy clusters collided about 150 million years ago. When they did, the hot gas in each cluster, visible in X-rays, slowed down and interacted, like two clouds of steam meeting and mixing. But the dark matter didn't slow down, passed right through. We can map where the mass is using gravitational lensing, the way mass bends light from background galaxies. And the mass is in a different place than the visible gas. The dark matter kept moving while the gas got left behind. It's direct evidence that dark matter exists as a separate substance from normal matter. And it's moving according to gravity, unaffected by the collisions and interactions that slow down gas and stars. Understanding dark matter's motion is crucial to understanding cosmic structure. Dark matter determines where galaxies form, how they cluster, and how they move. It's the invisible hand shaping the visible universe. Now let's zoom out further. Beyond galaxy clusters, beyond superclusters, to the largest scales we can observe. At these scales, something strange happens. The universe looks the same in every direction. This is called the cosmological principle. No matter where you are in the universe, no matter which direction you look, on average, you see the same thing. The same density of galaxies, the same large-scale structures, the same cosmic web. There's no center, no edge, no preferred location. This wasn't obvious. It's a profound statement about the nature of reality. The universe is homogeneous and isotropic on large scales. Homogeneous means the same everywhere. Isotropic means the same in all directions. And this uniformity is moving. The entire observable universe is expanding uniformly. Space itself is growing, carrying galaxies along with it. Edwin Hubble discovered this in 1929 when he found that distant galaxies are receding from us, and the farther away they are, the faster they're moving. Hubble's law: velocity equals the Hubble constant times distance. It's one of the most important equations in cosmology. It tells us the universe is expanding, and from that we can work backward to the Big Bang. But measuring the Hubble constant precisely has turned into one of the biggest controversies in modern cosmology. Different methods give different values, and the disagreement is getting harder to ignore. When we measure the expansion rate using the cosmic microwave background and the early universe, we get one number: about 67 kilometers per second per megaparsec. That means for every megaparsec, about 3.3 million light-years, the expansion adds 67 kilometers per second to a galaxy's recession velocity. But when we measure the expansion rate using nearby supernovae and Cepheid variable stars, we get a different number: about 73 kilometers per second per megaparsec. That's a 10% difference, and the uncertainties have gotten so small that the two measurements don't overlap. This is called the Hubble tension, and it's not going away. The more precise our measurements get, the more certain we are that there's a real disagreement. Either one of the methods has a systematic error we haven't found, or something is wrong with our model of the universe. Maybe dark energy isn't constant. Maybe it's changed over time. Maybe there's new physics we don't understand. Or maybe the cosmological principle is wrong, and the universe isn't as uniform as we thought. If the Hubble tension is real, it means the universe is expanding faster today than it was in the past, more than our current models predict. And that has implications for where everything is moving. It changes the age of the universe, the distances to faraway galaxies, the timeline of cosmic evolution. Right now, cosmologists are working frantically to resolve this. New telescopes, new observations, new techniques for measuring distances. The James Webb Space Telescope is helping, giving us unprecedented views of the early universe and allowing us to calibrate distance measurements with higher precision. But the tension remains, and it's exciting, because when observations disagree with theory, that's when we learn something new. That's when paradigms shift and our understanding deepens. Speaking of paradigms shifting, let's talk about the accelerating expansion. This discovery won the Nobel Prize in Physics in 2011, and it fundamentally changed our picture of the universe's fate. Before 1998, cosmologists thought the expansion of the universe was slowing down. Gravity pulls everything together, so it made sense that expansion would decelerate over time. The question was whether there was enough matter to eventually stop the expansion and cause a big crunch, or whether the universe would expand forever, just more and more slowly. Then two teams of astronomers studied distant supernovae, stellar explosions so bright they can outshine entire galaxies. Type Ia supernovae specifically. These explosions happen when a white dwarf star accumulates too much mass from a companion and collapses catastrophically. They're remarkably consistent in brightness, which makes them excellent standard candles for measuring cosmic distances. What the teams found shocked everyone. Distant supernovae were dimmer than expected. That meant they were farther away than they should be if the expansion was slowing down. The universe wasn't decelerating. It was accelerating. Something was pushing space apart, working against gravity, causing the expansion to speed up. They called it dark energy, and it's the biggest mystery in cosmology. Dark energy makes up about 70% of the total energy content of the universe. Dark matter is 25%. Normal matter, everything we can see and touch, is just 5%. We're living in a universe where 95% of the content is invisible and poorly understood. The simplest explanation for dark energy is Einstein's cosmological constant. Einstein added it to his equations of general relativity to keep the universe static, because he believed the universe was eternal and unchanging. When Hubble discovered the expansion, Einstein called it his biggest blunder and removed the constant. But it turns out he might have been right. A cosmological constant represents the energy of empty space itself. Quantum field theory predicts that even a vacuum has energy, virtual particles constantly popping in and out of existence. This vacuum energy would have a repulsive gravitational effect, pushing space apart. The problem is, when you calculate how much vacuum energy there should be based on quantum mechanics, you get a number that's 10 to the power of 120 times larger than what we observe. That's not a small error. That's the worst prediction in the history of physics. So either our calculation is catastrophically wrong, or dark energy is something else entirely. Maybe it's a new field, quintessence, that permeates space and changes over time. Maybe it's a sign that general relativity breaks down on cosmic scales. Maybe we're living in a multiverse, and our universe's vacuum energy is fine-tuned by chance. Nobody knows. But whatever it is, it's causing the universe to expand faster and faster, and that determines where everything is ultimately headed. Here's the trajectory. Right now, galaxies in our local group are bound by gravity. We're going to merge with Andromeda and form Milkomeda. The local group will eventually become a single giant galaxy. Other galaxy clusters will do the same. The Virgo cluster, the Fornax cluster, the Coma cluster, they'll all merge internally, forming massive elliptical galaxies. But beyond our local group, galaxy clusters are moving away from us, accelerating. Eventually, the space between clusters will expand so much that light from other clusters won't be able to reach us anymore. One by one, galaxies will disappear beyond the cosmic horizon. In about 100 billion years, any civilizations existing in Milkomeda will look out and see a dark sky. No other galaxies, no cosmic microwave background because it will have been redshifted into undetectable radio waves. Just their galaxy, alone in an empty universe. They'll have no evidence of the Big Bang. No way to know the universe is expanding. They might conclude they live in a static, eternal cosmos containing just their galaxy. They'd be wrong, but they'd have no way to know. This is called the Cosmic Dark Age, not to be confused with the first Dark Age when stars hadn't formed yet. In the far future, the universe will appear dark and empty, even though it's filled with the remnants of structure from our era. And it gets darker. After 100 trillion years, star formation will cease. The gas needed to make stars will be exhausted. Existing stars will burn out and die. The universe will be populated by white dwarfs, neutron stars, and black holes. After 10 to the 32 years, white dwarfs will cool to black dwarfs, cold cinders radiating nothing. After 10 to the 40 years, neutron stars and black dwarfs will collapse into black holes through rare quantum processes. By 10 to the 65 years, most matter will have fallen into black holes. The universe will be a collection of black holes drifting through expanding space. But even black holes don't last forever. Stephen Hawking showed that black holes radiate energy through quantum effects. They evaporate. A solar mass black hole takes 10 to the 67 years to evaporate. A supermassive black hole takes 10 to the 100 years. After 10 to the 100 years, even the largest black holes will have evaporated. The universe will consist of photons and elementary particles spreading through space, getting more and more dilute as expansion continues. This is the heat death. Maximum entropy. No gradients, no energy flows, nothing to drive any process. Just particles drifting through an ever-expanding void, getting colder and more spread out forever. It sounds bleak. The ultimate fate of everything in the universe is dissolution into nothingness. All the galaxies, stars, planets, everything we see and everything we are, will eventually decay and disappear. But remember, this is trillions upon trillions of years in the future. Timescales that make the current age of the universe look like the blink of an eye. We're living in the universe's infancy, the brief era when stars shine and structure exists. And there's something profound in that. The universe's motion, from the Big Bang through the formation of structure and into the far future, follows the laws of physics. Those laws are comprehensible. We can write them down, test them, use them to predict the future and reconstruct the past. The fact that we can understand where everything is moving, where it came from, and where it's going, that's extraordinary. A pattern of atoms and energy, temporarily organized into a conscious mind, able to trace the motion of galaxies billions of light years away and predict the fate of the cosmos trillions of years hence. Let's bring this to something more immediate: the motion of our solar system through the Milky Way. We're located about 26,000 light-years from the galactic center, in the Orion Arm, a minor spiral arm between the Perseus and Sagittarius arms. Our orbit around the galaxy is roughly circular, but not perfectly so. We bob up and down through the galactic plane, oscillating like a cork on water. Right now, we're about 60 light-years above the galactic plane and moving upward. We'll reach our maximum height, about 250 light-years above the plane, in about 13 million years. Then we'll fall back down, cross through the plane, reach 250 light-years below it, and come back up. The full cycle takes about 60 million years. This has consequences. When we're in the galactic plane, we pass through denser regions of gas and dust. The increased material can trigger comet showers from the Oort cloud, potentially causing extinction events on Earth. Some scientists have linked mass extinctions to our passage through the galactic plane, though the evidence is controversial. We're also moving relative to our local stellar neighborhood. The Sun is traveling at about 44,000 miles per hour relative to nearby stars. We're heading toward a point in the constellation Hercules, carrying Earth and the other planets with us. In about 30,000 years, we'll pass within about 3 light-years of a star called Gliese 710. That's close, astronomically speaking. Its gravity might disturb the Oort cloud, sending comets toward the inner solar system. It won't threaten Earth directly, but it's a reminder that stellar motion has consequences. Stars are constantly moving past each other in the galaxy. The Sun formed in a stellar nursery with thousands of other stars about 4.6 billion years ago. Those sibling stars have long since drifted apart, scattered across the Milky Way by gravitational interactions. We have no idea where most of them are now. Some might have passed near us since then. Others might pass near us in the future. The galaxy is a dynamic place, with stars following complex orbits, sometimes approaching, sometimes receding, always in motion. And the Milky Way itself is evolving. It's been eating smaller galaxies. Right now, the Sagittarius dwarf elliptical galaxy is being torn apart by our galaxy's gravity, its stars streaming out in long tidal tails. Over the next few 100 million years, it will be completely absorbed. We've done this before. The thick disk of our galaxy, the puffed-up layer of older stars surrounding the thin disk, formed from ancient galactic mergers. Billions of years ago, the Milky Way collided with smaller galaxies. Their stars stirred up and added to our galaxy's population. Astronomers can identify these ancient collisions by looking at stellar chemistry and orbits. Stars from merged galaxies have different compositions and move in different directions than stars born in the Milky Way. It's galactic archaeology, reading the history of our galaxy in the motion and composition of its stars. And then there's the Andromeda collision. 4.5 billion years from now, our galaxies will merge. Simulations show it won't be a single collision but a series of close passes, each one distorting both galaxies, flinging out stars and gas in long tidal streams. The supermassive black holes at the centers of each galaxy, Sagittarius A star in the Milky Way and the larger black hole in Andromeda, will spiral toward each other, eventually merging in a cataclysmic release of gravitational waves that will ripple through spacetime. But individual stars rarely collide. Space is mostly empty. Even in the densest regions of a galactic merger, stars pass by each other with room to spare. The night sky will change dramatically, new stars and nebulae appearing as the galaxies intermingle, but Earth itself will likely survive unscathed. Unless we get ejected, there's a small chance that during the merger, the Sun and its planets could be flung out into intergalactic space, exiled from the newly formed Milkomeda. We'd become a rogue solar system, drifting through the darkness between galaxies. If that happened, Earth would still orbit the sun. We'd still have warmth and light, but the night sky would be empty. No Milky Way, no Andromeda, just Milkomeda in the distance, a faint smudge of light, getting fainter as we drift farther away. It's unlikely. Most stars stay within the merged galaxy, but it's a possibility, a reminder that motion in the universe has consequences we can't fully predict. Now, let's talk about something truly strange. Frame dragging and the rotation of spacetime itself. Massive rotating objects twist spacetime around them. It's called frame dragging or the Lense-Thirring effect. Near a spinning black hole, space itself rotates, dragged along by the black hole's angular momentum. This isn't a metaphor. Spacetime is a physical thing, and it can be twisted, stretched, and dragged. If you tried to hover motionless near a rotating black hole, you'd find yourself being pulled around it, not by a force, but by the rotation of spacetime itself. The ergosphere is the region around a rotating black hole where this effect is so strong that nothing can remain stationary. Even light is dragged along. To hover in the ergosphere, you'd have to travel faster than light, which is impossible. So everything in the ergosphere must rotate with the black hole. You can extract energy from this. It's called the Penrose process. Drop something into the ergosphere, and if you do it right, you can get more energy out than you put in. The energy comes from the black hole's rotation, slowing it down incrementally. Advanced civilizations might use this to power themselves. A Dyson sphere around a rotating black hole could harvest its rotational energy for trillions of years, long after the last stars have burned out. But that's speculation. What's certain is that rotation affects motion in profound ways. Every rotating object, from planets to galaxies, drags spacetime around with it. The effect is tiny for small masses like Earth, but it's measurable. Gravity Probe B, a NASA satellite launched in 2004, confirmed frame dragging around Earth with high precision. This means the motion of satellites around Earth is affected not just by Earth's mass, but by its rotation. GPS satellites experience tiny shifts in their orbits due to frame dragging. We have to account for it to keep GPS accurate. On galactic scales, frame dragging could affect how galaxies rotate and how stars orbit. It's a small effect, but in a universe where we're trying to account for every bit of matter and motion, small effects matter. Speaking of galactic rotation, there's another mystery: spiral arms. If you look at a spiral galaxy, you see beautiful arms curving out from the center, glowing with young stars and bright nebulae. They look solid, like they're rotating as rigid structures. But they're not. Stars don't move with the spiral arms. They move through them. The arms themselves are density waves, regions where stars and gas bunch up temporarily before moving on. It's like a traffic jam on a highway. Cars slow down in the jam, then speed up and move past it. The jam itself might not move much, even though cars are constantly flowing through it. Spiral arms are stellar traffic jams. As stars and gas move through these dense regions, they interact gravitationally, slowing down slightly. Gas clouds collide and compress, triggering star formation. That's why spiral arms are bright with young stars. But the arms themselves rotate at a different speed than the stars. This is called density wave theory, and it explains why spiral structure persists even though individual stars move through it. The motion of stars in spiral galaxies is complex. Some stars have nearly circular orbits. Others have elliptical orbits that take them closer to and farther from the galactic center. When these orbits align in certain ways, they create resonances that reinforce the spiral pattern. And here's the strange part. We still don't fully understand what maintains spiral structure. Some galaxies have grand design spirals with two prominent arms. Others have flocculent spirals with many small, fragmented arms. The patterns are influenced by gravitational interactions with nearby galaxies, dark matter distribution, and the galaxy's rotation rate. The Milky Way probably has 4 major spiral arms, though there's debate. We're inside the galaxy looking out through dust and stars, so mapping our own structure is harder than mapping external galaxies. But we know we're moving through a spiral arm right now. The Orion arm where we're located might be a spur between larger arms, or it might be a distinct arm in its own right. The stars around us, the nebulae visible in the night sky, are our companions in this journey through the spiral structure. And that journey is ancient. The Sun has orbited the Milky Way about 20 times since it formed. We've been through the spiral arms, through the interarm regions, up and down through the galactic plane over and over for billions of years. Each orbit takes about 230 million years. Dinosaurs appeared and went extinct in less than 1 galactic year. Human civilization, all of recorded history, is a tiny fraction of a single orbit. Put another way, the last time we were in this position in the galaxy, the supercontinent Pangaea was forming. The continents we know today didn't exist yet. Life was primarily in the oceans. The Permian extinction, the worst mass extinction in Earth's history, hadn't happened yet. 1 orbit before that, primitive amphibians were crawling onto land for the first time. Trees were a new innovation. The Earth's atmosphere was still adjusting to the oxygen produced by photosynthetic life. Go back 20 orbits to when the Sun first formed, and Earth didn't exist. The solar system was a disk of gas and dust, slowly coalescing into planets. Over the next several orbits, planets formed, were bombarded by asteroids and comets, and eventually stabilized. Life emerged on Earth during one of those early orbits, about 3.5 billion years ago. Since then, we've circled the galaxy about 15 times, and life has evolved from single cells to the incredible diversity we see today. All while moving through the galaxy at 500,000 miles per hour. The motions we're discussing aren't abstractions. They're the context in which everything happens. Life evolved in a solar system that's been traveling through different stellar neighborhoods, exposed to varying levels of cosmic rays, occasionally passing through dense molecular clouds. Some scientists think our journey through the galaxy has influenced evolution. Cosmic rays, high-energy particles from space, can cause mutations. When the solar system passes through the galactic plane or through a spiral arm, we might encounter higher levels of radiation. There's even a hypothesis that mass extinctions correlate with our galactic orbit. Every 30 million years or so, as we pass through certain regions of the galaxy, extinction rates spike. The evidence is weak, and many scientists are skeptical, but it's an intriguing idea. Our motion through space might be written in the fossil record. What's certain is that the Sun's journey affects the environment around us. We're currently in a region of space called the local bubble, a cavity about 1,000 light-years across carved out by ancient supernova explosions. The hot, thin gas inside the bubble creates a relatively quiet environment, shielding us from some of the galactic background radiation. But we won't stay here forever. In a few million years, we'll move out of the local bubble and into denser regions of the galaxy. The interstellar environment around the solar system will change. More gas, more dust, more radiation. The shape and extent of the heliosphere, the bubble of solar wind that protects the planets, might shrink or expand in response. These changes won't threaten Earth directly. We're protected by our atmosphere and magnetic field. But they'll affect the space environment, potentially influencing climate through cosmic ray interactions with the atmosphere. The point is, we're not isolated. We're part of a galaxy in motion, and that motion has consequences. Now let's zoom back out to the motion of galaxy clusters and the flow of the cosmic web. Galaxy clusters are the largest gravitationally bound structures in the universe. The Virgo cluster, our nearest large cluster, contains about 1,500 galaxies and has a total mass equivalent to 10 to the 15th solar masses. That's 1,000,000 billion suns worth of matter. The cluster is falling toward us at about 1,000 kilometers per second. Or rather, we're falling toward it. The local group and the Virgo cluster are part of the larger Virgo supercluster, and we're all moving together through the cosmic web. But even the Virgo supercluster is part of something bigger, Laniakea. And Laniakea is flowing toward other concentrations of mass in the universe. To map these flows, astronomers measure peculiar velocities. They look at galaxies, determine how fast they're moving away due to cosmic expansion, then subtract that to find the galaxy's individual motion. What's left is the peculiar velocity, the motion due to gravity pulling it toward or away from nearby mass concentrations. By measuring thousands of galaxies, we can map the flow of matter through space. And what we find is a hierarchy of motion. Small galaxies fall into larger galaxies. Galaxy groups fall into clusters. Clusters fall into superclusters. And superclusters flow along the filaments of the cosmic web toward the densest nodes. It's like water flowing downhill, except the hills are made of dark matter and the water is galaxies. The cosmic web is a drainage system on the largest scales, with matter flowing from voids into filaments and from filaments into clusters. The voids themselves are interesting. They're not completely empty, but they're close. The density inside a void is about 10% of the average density of the universe. That might not sound like much of a difference, but it's enough to create distinct environments. Galaxies in voids are different from galaxies in clusters. They tend to be smaller, bluer, and more actively forming stars. They haven't experienced the violent interactions and mergers common in clusters. They're lonely and isolated, drifting through nearly empty space. And voids are expanding faster than average. Because they have less matter, dark energy dominates more strongly. The expansion of space inside voids is accelerating faster than in regions with more matter. Over time, voids grow larger and emptier, while filaments and clusters grow denser. This is the fate of the cosmic web. Over billions of years, matter concentrates more and more into the densest regions, while voids expand and become emptier. Eventually, the universe will consist of isolated galaxy clusters surrounded by enormous voids. And then, as dark energy continues to dominate, even those clusters will dissolve as galaxies accelerate away from each other. But that's billions of years away. For now, the cosmic web is a dynamic, evolving structure, and we're part of it. Our position in the web isn't special. We're in a filament, moving through it like countless other galaxies. But from our perspective, we can map the entire structure, see how it fits together, understand the forces shaping it. And that brings us to a subtle but important point. When we talk about where everything is moving, we have to ask, moving relative to what? In everyday life, motion is relative to the ground or to other objects around us. But in cosmology, there's no absolute reference frame. The universe doesn't have a background grid against which motion can be measured. Einstein taught us this. The laws of physics are the same in all inertial reference frames. There's no experiment you can do to determine absolute motion. You can only measure motion relative to something else. But there's one reference frame that's special in cosmology. The reference frame in which the cosmic microwave background is isotropic, the same in all directions. In our actual reference frame, moving through space at hundreds of thousands of miles per hour, the CMB is slightly blue-shifted in the direction we're moving and red-shifted in the opposite direction. We call this the dipole anisotropy. It's been measured with incredible precision. The Earth is moving at about 370 kilometers per second relative to the CMB in the direction of the constellation Leo. That motion is the sum of all our individual motions. Earth orbiting the Sun orbiting the galaxy falling toward the Great Attractor, everything combined into a single velocity relative to the CMB. In a sense, the CMB defines a universal rest frame, not because it's special in the laws of physics, but because it's the oldest light in the universe, coming from everywhere, providing a reference against which we can measure our motion. And our motion through the CMB has consequences. It creates a small asymmetry in the universe as we observe it. The sky looks slightly different depending on which direction we look, not because the universe is asymmetric, but because we're moving through it. This is important for cosmology. When we measure the properties of the early universe using the CMB, we have to account for our motion. We have to subtract out the dipole to get to the underlying signal. And when we do that, we find that the universe is remarkably uniform. The temperature variations in the CMB are only about 1 part in 100,000. That's astonishingly smooth. But those tiny variations are crucial. They're the seeds of structure. The slightly hotter regions had slightly higher density. Over time, they grew into galaxies and galaxy clusters. The cooler regions became voids. We can trace a direct line from those quantum fluctuations in the infant universe to the motion of galaxies today. The patterns we see in the CMB predict the patterns we see in the cosmic web. It's a perfect validation of our cosmological models. But there are anomalies. Some features in the CMB that we don't fully understand. The cold spot, for example, a region larger than expected that's about 70 microkelvins colder than average. It could be a statistical fluke. Or it could be evidence of something exotic, like a collision with another universe bubble. There's also the axis of evil, an unfortunate name for an alignment of features in the CMB that seems to point in a particular direction in space. It shouldn't be there. The cosmological principle says the universe should be isotropic, the same in all directions. But some of the largest patterns in the CMB seem to be aligned. Most cosmologists think these are statistical anomalies or artifacts of how we process the data. But a few wonder if they're hints of something deeper. Maybe the universe isn't perfectly isotropic. Maybe our observable universe is a small patch of a larger structure that has a preferred direction. If that's true, it would change everything. It would mean our motion through the universe isn't random. We'd be moving through a structured cosmos with directions that matter. But the evidence is weak. And Occam's razor suggests the simplest explanation is usually correct. The universe is probably isotropic, and the anomalies are just noise. Still, it's worth investigating, because every time we found something unexpected in astronomy, it's led to new discoveries. Quasars, pulsars, dark matter, dark energy, gravitational waves. All of them started as anomalies that didn't fit existing theories. So we keep looking, keep measuring, keep questioning, and that brings us to gravitational waves. Ripples in space-time itself traveling at the speed of light. When massive objects accelerate, they distort space-time, and those distortions propagate outward as waves. Einstein predicted them in 1916, but they weren't detected until 2015, when LIGO observed two black holes colliding. The signal was unmistakable. A chirp, increasing in frequency as the black holes spiraled closer together. Then a final peak as they merged, followed by ring-down as the newly formed black hole settled into a stable shape. That chirp encoded information about the masses and spins of the black holes, their distance from us, and even the orientation of their orbital plane. It was like hearing the universe for the first time. Since then, we've detected dozens of gravitational wave events. Merging black holes, merging neutron stars, possibly even merging black holes and neutron stars. Each detection teaches us something new about the population of compact objects in the universe. But gravitational waves also tell us about motion. When two massive objects orbit each other, they emit gravitational waves, carrying away energy. This causes the orbit to decay, making the objects spiral closer together. Eventually, they merge. This is happening all over the universe. Binary star systems, binary black holes, binary neutron stars, all slowly losing energy to gravitational waves and spiraling inward. Over millions or billions of years, they'll merge, releasing a burst of gravitational waves in their final moments. And those waves travel through space, passing through galaxies, through dark matter, through everything, barely interacting with anything. They're messengers from the most violent events in the universe. But there's another source of gravitational waves we haven't detected yet: the cosmic gravitational wave background. Just like the cosmic microwave background is the leftover light from the Big Bang, there should be a cosmic gravitational wave background from the earliest moments of the universe. Gravitational waves produced during inflation, or during phase transitions in the primordial plasma, or from cosmic strings if they exist. These waves would be incredibly faint, far below what current detectors can measure. But future detectors like LISA, the Laser Interferometer Space Antenna, might be able to detect them. LISA will be 3 spacecraft flying in formation 1,000,000 kilometers apart, using lasers to measure tiny changes in their separation caused by passing gravitational waves. If we detect the cosmic gravitational wave background, it would be revolutionary. It would give us a direct view of the universe when it was younger than a second old, far earlier than the CMB, which shows the universe at 380,000 years old. We could test theories of inflation, probe the fundamental physics of the early universe, maybe even detect evidence of extra dimensions or exotic particles. The cosmic gravitational wave background is a treasure trove waiting to be discovered. And it would tell us about motion at the very beginning, about how space-time itself was rippling and churning in those first moments, about the quantum foam from which everything emerged. But even without detecting those primordial waves, gravitational wave astronomy is transforming our understanding of the universe. We're now observing the cosmos with multiple messengers: light, neutrinos, cosmic rays, and gravitational waves. Each one tells us something different. Light shows us the hot and bright parts of the universe. Neutrinos show us processes inside stars and supernovae where light can't escape. Cosmic rays show us the most energetic particle accelerators in nature. And gravitational waves show us the most massive and violent motions, the collisions and mergers that shape the universe. Together, these messengers give us a complete picture. And that picture is one of motion. Everything is moving, accelerating, colliding, merging, flowing through space according to the laws of physics. Now let's talk about something closer to home but equally profound: the motion of objects within our own solar system. The planets orbit the sun in ellipses, as Kepler discovered 400 years ago. But those orbits aren't static. They change over time due to gravitational interactions with other planets. Jupiter, the giant of the solar system, has a mass 2.5 times that of all the other planets combined. This gravity perturbs every other planet's orbit. Earth's orbit, for example, varies in eccentricity over a 100,000-year cycle due to Jupiter's influence. This affects our climate. The more elliptical Earth's orbit, the greater the difference between summer and winter, combined with variations in Earth's axial tilt and precession. These orbital changes drive ice ages and warm periods. They're called Milankovitch cycles, and they're written in the geological record. So Jupiter's motion affects Earth's climate. We're connected by gravity, our motions coupled across hundreds of millions of miles of space. The other planets have similar effects. Venus and Jupiter together cause Earth's axial tilt to vary between 22 and 24 degrees over a 41,000-year period. Mars, despite being smaller, has a chaotic axial tilt that swings wildly over millions of years because it doesn't have a large moon to stabilize it. The moon, in fact, is slowly moving away from Earth, about 1.5 inches per year. Tidal interactions transfer angular momentum from Earth's rotation to the moon's orbit, causing Earth's day to lengthen and the moon to recede. 4 billion years ago, the moon was much closer, and Earth's day was only about 6 hours long. The moon appeared huge in the sky, raising enormous tides that sloshed around the planet. Over time, those tides have slowed Earth's rotation and pushed the moon outward. In about 2 billion years, the moon will be far enough away that total solar eclipses will no longer occur. The moon will appear too small to cover the sun completely. We're living in a special time when the moon and sun appear almost exactly the same size in the sky, creating perfect eclipses. But even this motion is temporary. Eventually, the moon will reach a maximum distance and stop receding. Earth's rotation will slow to match the moon's orbital period, and both will be tidally locked, always showing the same face to each other. An Earth day will equal a lunar month, both about 47 current days long. But before that happens, the sun will become a red giant and destroy both Earth and the moon. So the final state of tidal locking will never be reached. Farther out in the solar system, things get more chaotic. The asteroid belt between Mars and Jupiter is full of objects in complex, overlapping orbits. Some asteroids are in stable orbits that haven't changed much in billions of years. Others are in chaotic orbits that shift unpredictably. Resonances with Jupiter play a major role. An asteroid in a 2-to-1 resonance with Jupiter orbits the Sun twice for every one Jupiter orbit. These resonances can stabilize or destabilize orbits depending on the details. The Kirkwood gaps in the asteroid belt are regions where resonances with Jupiter have cleared out asteroids. If an asteroid drifts into one of these resonances, its orbit becomes chaotic, eventually leading to a collision with a planet or ejection from the solar system. Some asteroids end up on Earth-crossing orbits. These are the potentially hazardous asteroids that could impact our planet. We're tracking thousands of them, calculating their orbits, assessing the risk. The dinosaurs were wiped out by one such impact 66 million years ago. A 6-mile-wide asteroid hit what's now the Yucatan Peninsula, releasing energy equivalent to billions of nuclear bombs. The impact threw up debris that blocked sunlight, caused global cooling, and disrupted ecosystems worldwide. That asteroid had been orbiting the sun for billions of years, its motion slowly changing due to gravitational interactions and thermal effects, until finally its path crossed Earth's at the wrong moment. Motion has consequences. Out beyond Neptune lies the Kuiper Belt, a region of icy bodies left over from the solar system's formation. Pluto is the most famous, but there are thousands of others, some nearly as large. These objects have highly eccentric orbits. Many are in resonances with Neptune. Some have been scattered into the Oort cloud, a vast spherical shell of comets surrounding the solar system. The Oort cloud extends about a light year from the Sun, halfway to the nearest star. It's loosely bound by the Sun's gravity, so passing stars can disturb it, sending comets falling toward the inner solar system. When we see a comet with a multimillion-year orbital period, it's likely from the Oort cloud, knocked loose by a stellar encounter and now making a one-time journey through the inner solar system. After it rounds the Sun, it might return to the Oort cloud, or it might be ejected entirely, becoming an interstellar object. We've recently detected interstellar objects passing through our solar system. Oumuamua in 2017 and Borisov in 2019. These are objects from other star systems, wandering through the galaxy, occasionally passing through our neighborhood. Oumuamua was strange. It accelerated slightly as it left the solar system, more than could be explained by solar gravity alone. The most likely explanation is outgassing, like a comet, but we didn't see any gas or dust coming off it. Some scientists suggested exotic explanations, like a light sail from an alien civilization. Most think it's just a comet with unusual properties, but it reminded us that space is full of objects we don't understand, moving on trajectories we can barely predict. Every object in the solar system, from Mercury to the most distant Oort cloud comet, is moving in a complex dance governed by gravity. And that dance has been going on for 4.5 billion years, ever since the solar nebula collapsed and formed the Sun and planets. The motions we see today are the result of that initial collapse, modified by billions of years of gravitational interactions. It's a system in motion, never static, always evolving. And it's part of the larger motion of the solar system through the galaxy, which is part of the motion of the galaxy through the local group, which is part of the motion of the local group through Laniakea, which is part of the expansion of the universe. Scales within scales, motions within motions. Let's talk about something that ties it all together: the principle of least action. In physics, there's a deep principle that governs motion. Systems evolve along paths that minimize the action, a quantity that depends on energy and time. It's a strange concept, but it's incredibly powerful. You can derive Newton's laws from the principle of least action. You can derive general relativity from it. Quantum mechanics, electromagnetism, all of fundamental physics can be expressed in terms of action. And what it tells us is that motion isn't random. Objects follow specific paths through space and time because those paths minimize action. A planet orbits the Sun in an ellipse because that's the path of least action. Light bends around a massive object because that's the shortest path through curved spacetime. There's a kind of inevitability to it. Given the initial conditions and the laws of physics, everything that happens is determined. The motion of galaxies, the formation of stars, the evolution of the universe, all of it follows from the principle of least action. But here's where it gets philosophical. Does that mean the universe is deterministic? That everything was set in motion at the Big Bang and has been following a predetermined path ever since? Not quite. Quantum mechanics introduces randomness at the fundamental level. When a radioactive atom decays, or when a photon chooses which path to take, there's genuine randomness. The outcome isn't determined by prior conditions. It's probabilistic. So the universe is deterministic in the large but random in the small. The motion of galaxies follows predictable laws. The motion of individual particles has an element of chance. And yet, from quantum randomness, order emerges. Stars form, planets coalesce, life appears. The universe is both chaotic and ordered, random and structured, unpredictable and lawful. It's this interplay between determinism and randomness that makes the universe interesting. If everything were completely deterministic, the universe would be boring, mechanical, predictable. If everything were completely random, there would be no structure, no patterns, nothing to understand. But we live in a universe that's poised between the two. Deterministic enough to have laws and patterns, random enough to have novelty and complexity, and motion is at the heart of it. Things move because of forces and fields. They interact because they're in motion. Complexity arises because moving systems can organize themselves into structures that persist and evolve. Life itself is a motion phenomenon. Cells move molecules around, extracting energy from their environment, maintaining themselves far from equilibrium. Organisms move through space, seeking resources, avoiding danger. Evolution is motion through the space of possible genetic configurations. Even thought is motion. Neurons firing, signals propagating, patterns forming and dissolving in the brain. Consciousness emerges from the motion of matter and energy organized in just the right way. So when we ask where everything is moving, we're asking one of the deepest questions possible. We're asking about the fundamental nature of reality, about how the universe evolves, about our place in the grand scheme of things. And the answer is breathtaking in its scope. Everything is moving because the universe began in motion and hasn't stopped. From the first instant of the Big Bang, through the formation of atoms and stars and galaxies, to the present moment and beyond, motion is the thread connecting it all. We're part of that motion, not observers standing outside the universe looking in, but participants embedded in the flow. We move with the Earth, with the Sun, with the galaxy. We're made of atoms that have been moving through the cosmos for billions of years. And we have the capacity to understand it, to measure the speeds of galaxies, calculate their trajectories, predict their futures, to trace our motion back to the Big Bang and forward to the heat death of the universe. That's extraordinary. A collection of atoms, temporarily organized into a thinking being, able to comprehend the motion of the entire cosmos. It's humbling and empowering at the same time. Humbling because we're so small, so brief, so utterly insignificant on cosmic scales. Empowering because we can understand, we can know, we can map the universe and our place in it. So where is everything moving? In the directions determined by gravity, by momentum, by the expansion of space, by the laws of physics written into the fabric of reality itself. But also toward greater complexity, toward structure and order, toward the possibility of understanding. Because in the end, motion isn't just about trajectories and velocities. It's about change, about evolution, about the universe becoming something it wasn't before. Galaxies collide and merge, forming new structures. Stars are born and die, creating heavy elements. Planets form and host life. Intelligence emerges and contemplates its own existence. The universe is moving from simplicity to complexity, from uniformity to structure, from unconsciousness to awareness. And we're here to witness it, to be part of it, to add our own small motion to the grand cosmic flow. Every breath you take moves atoms that were once in stars. Every step you take participates in the Earth's rotation. Every thought you think ripples through the electrochemical fabric of your brain, a tiny echo of the energy flows that power the universe. You're not separate from the cosmos. You're made of it, and you're moving with it, always have been, always will be, until your atoms scatter and join the next generation of stars and planets and, perhaps, living things. That's the ultimate answer to where everything is moving. Toward the future, toward whatever comes next, toward possibilities we can barely imagine. The universe is 13.8 billion years old. It will exist for trillions upon trillions of years more. We're living in the first tiny fraction of its existence, the age when stars shine and galaxies cluster and life explores the cosmos. It won't last forever. Dark energy will win. The universe will expand into cold darkness. But not yet. Not for a very long time. Right now, we're here, moving at 1,000,000 miles per hour through space, orbiting a star that's orbiting a galaxy that's falling toward other galaxies in an expanding universe, caught up in flows of matter and energy that started at the Big Bang and will continue until the heat death. And somehow we know this. We've figured it out. We've measured it. We've mapped it. That's the real miracle. Not that the universe is in motion, but that we can understand the motion. That the laws governing galaxies billions of light years away are the same laws we can test in laboratories here on Earth. That mathematics, a language invented by human minds, can describe the behavior of the entire cosmos. It suggests something profound. That the universe is comprehensible. That reality follows rules. That despite its vast size and age and complexity, it's not arbitrary or random, but ordered and lawful. And if we can understand where everything is moving, what else can we understand? What other mysteries can we solve? What other secrets can we uncover? The history of science is a history of expanding knowledge. We started by wondering about the stars. Now we know they're distant suns. We wondered about the Milky Way. Now we know it's one of trillions of galaxies. We wondered about motion. Now we can trace the trajectory of every object in the observable universe back to the Big Bang. What will we know in 100 years? In 1,000? If civilization survives and continues to explore and discover, what wonders will we uncover? Maybe we'll detect the cosmic gravitational wave background and probe the first moments of creation. Maybe we'll find life on other worlds and learn we're not alone. Maybe we'll develop new physics that explains dark matter and dark energy. Maybe we'll even find a way to survive the heat death, to persist in some form long after the stars go out. Or maybe we'll destroy ourselves. Climate change, nuclear war, engineered pandemics, artificial intelligence gone wrong. The universe doesn't care. It will keep moving whether we're here or not. But for now, we are here, and we have a choice. We can squander our brief moment in the cosmic spotlight, fighting over resources and ideologies. Or we can embrace our role as the universe's way of understanding itself. We can explore. We can discover. We can create. We can try to preserve this fragile bubble of consciousness in a vast, indifferent cosmos. Because motion is inevitable. The universe will keep expanding. Galaxies will keep colliding. Stars will keep forming and dying. But understanding is not inevitable. It requires consciousness, curiosity, effort. We're the only beings we know of who can trace the motion of galaxies, who can predict the collision of black holes, who can map the cosmic web and calculate the fate of the universe. That's a responsibility and an opportunity. So when you look up at the night sky, remember that you're not looking at something static and eternal. You're looking at a universe in motion, a cosmos that's been evolving for nearly 14 billion years and will continue evolving for trillions more. And you're part of that motion. Every atom in your body has a history that spans the lifetime of the universe. You're made of hydrogen from the Big Bang, carbon from ancient stars, iron from supernovae. You're a temporary pattern in the flow of matter and energy through space and time. A brief eddy in the cosmic current. A moment of complexity and awareness in a universe that's mostly empty and unconscious. But what a moment! What an incredible, improbable, precious moment. Because right now, in this instant, you exist. You think. You wonder. You ask questions about where everything is moving. And you can find answers. You can understand. You can know your place in the cosmos. That's the gift of consciousness. The ability to step back and see the big picture. To comprehend your own motion through space and time. To recognize that you're part of something vast and ancient and ongoing. So cherish it. Use it. Add to humanity's understanding of the universe. Or just appreciate it. Marvel at it. Let it fill you with wonder. Because we're living in an extraordinary time. A time when we can see farther than ever before, understand more than ever before, ask bigger questions than ever before. We're living in a universe that's revealing its secrets, slowly but surely, to anyone curious enough to look. And what we've found is motion. Everywhere, at every scale, from the smallest particles to the largest structures, everything is moving. Not randomly, not chaotically, but according to laws, following patterns, creating structures that persist and evolve. The universe is a symphony of motion, and we're part of the orchestra, so play your part. Move through life with purpose and curiosity. Explore, discover, create, connect, because you're not just moving through space, you're moving through time, and time, unlike space, only goes one direction, forward, toward whatever comes next. Make it count. Where is everything in the universe moving? Toward the future. Always toward the future. And the future is unwritten. It depends on what we do, what we discover, how we choose to live. The cosmos will keep expanding. Galaxies will keep colliding. Stars will keep forming and dying. But whether consciousness survives, whether understanding deepens, whether the universe comes to know itself more fully, that depends on us. We're the universe becoming aware of itself. And that awareness, that understanding, that capacity to ask where everything is moving and find answers, that's the most remarkable motion of all. So keep moving, keep asking, keep wondering, because the journey isn't over. It's just beginning. And who knows where we'll go next?